Active epilepsy or seizure, as this person is experiencing, and other harmful brain damage, affects millions around the world. In the United States, approximately 3.4 million people have active epilepsy. Additionally, in 2017, there were around 224,000 hospitalizations related to traumatic brain injuries in the US, resulting in 61,000 deaths. Currently, doctors use electroencephalography, EEG, with critically ill patients to detect seizures and other types of brain activities that can cause brain damage. However, are you aware that in today's world, EEG monitoring largely relies solely on manual analysis by specialized neurologists? According to the World Health Organization, epilepsy is the most common chronic brain disease and affects people of all ages. More than 50 million people worldwide have epilepsy. Nearly 80% of them live in low and middle-income countries. An estimated 70% of people with epilepsy could be seizure-free if properly diagnosed and treated. However, about 3/4 of people with epilepsy in low-income countries do not get the treatment they need, and this rises to 90% in some countries. In many such countries, many health professionals do not have the training to recognize, diagnose and treat epilepsy. Recently, the Sunstella Foundation, Persist, Jazz Pharmaceuticals, and the Clinical Data Animation Center, CDAC, group completed a competition on Kaggle. The competition's goal was for data scientists from around the world to compete to develop an AI model trained on electroencephalography, EEG, signals recorded from critically ill hospital patients to detect and classify seizures and other types of harmful brain activities. The competition had 17,133 entrants, 3,507 participants and 2,767 teams, making 62,509 submissions. However, a search on the discussions forum of the competition revealed that none of the submissions seemed to have used a distributed computing with Apache Spark big data approach. In this case study, we are going to look at an approach based on distributed computing and big data using Apache Spark with PySpark ML for AI/ML models for seizure detection. We will provide an alternative distributed computer AI approach to help rapidly improve electroencephalography pattern classification accuracy, unlocking transformative benefits for neurocritical care, epilepsy, and drug development. By engaging with doctors and brain researchers, we can provide them with our approach to help detect seizures or other brain damage to provide faster and more accurate treatments. A significant aspect of practicing medicine is for a doctor to take vital signs, data, and interpret the data to arrive at the correct diagnosis and subsequently a successful treatment. When you take someone who you love or someone who you presume is having or having had a seizure to the doctor, how do doctors detect and classify if a seizure has occurred or is occurring in that person? The Sunstella Foundation, Persist, Jazz Pharmaceuticals, and the Clinical Data Animation Center, CDAC, undertakes research that is aimed at helping to preserve and enhance brain health. However, these specialized neurologists' work is a labor-intensive process and a major bottleneck. Not only can it be time-consuming, but manual review of EEG recordings is also expensive, prone to fatigue-related errors, and suffers from reliability issues between different reviewers, even when those reviewers are experts.
The good news is that things are changing. Groundbreaking advancement is underway where artificial intelligence, AI, and machine learning, ML, are being harnessed to analyze and interpret electroencephalography, EEG, signals. These signals, recorded from critically ill patients in hospitals, hold vital information about brain activity, especially during seizures and other harmful episodes. By training sophisticated AI and ML models with these EEG signals, researchers and doctors are able to detect and classify different patterns of brain activity accurately. The application of AI and ML in EEG analysis is revolutionizing neurocritical care, epilepsy treatment, and even drug development. Through cutting-edge technology, these models can enhance the accuracy of classifying EEG patterns, enabling healthcare professionals to intervene swiftly and effectively in cases of brain anomalies. Among the various types of brain activity patterns that are of interest in this field, 6 primary categories stand out. 1. Seizure, SZ. The detection of seizure activity in EEG signals is of paramount importance. By being able to accurately identify seizure patterns, medical professionals can administer appropriate and timely treatment to patients experiencing seizures. 2. Generalized periodic discharges. These recurring discharges in the brain can indicate critical conditions that require immediate attention. Recognizing this pattern through AI analysis can assist in diagnosing and treating patients effectively. 3.
Lateralized periodic discharges, LPD. LPDs are a specific type of brain activity that occurs predominantly on one side of the brain. Detecting and classifying LPDs can provide valuable insights into the patient's condition and guide treatment decisions. 4. Lateralized rhythmic delta activity, LRDA. LRDA is characterized by rhythmic delta waves on one side of the brain. Identifying LRDA patterns through AI-powered analysis can help clinicians in diagnosing certain neurological disorders and planning appropriate interventions. 5. Generalized rhythmic delta activity, GRDA. GRDA involves rhythmic delta wave activity across the entire brain. Analyzing and categorizing GRDA patterns using AI algorithms can contribute to a more comprehensive understanding of the patient's brain health and aid in personalized treatment strategies. 6. Other. The catch-all category of Other encompasses a range of EEG patterns that do not fit neatly into the above classifications. AI and ML models can assist in sorting and categorizing these diverse patterns, providing valuable insights for medical professionals. By leveraging AI and ML technologies to analyze EEG signals and detect these specific patterns of brain activity, healthcare providers and researchers are paving the way for more precise diagnostics, tailored treatments, and improved patient outcomes. The ability to swiftly identify seizures, abnormal brain activity, and potential neurological issues through advanced EEG analysis holds the promise of transforming the landscape of neurocritical care and brain research. To develop our AI/ML prediction model against classified seizure types, we will use labeled data as shown on the screen. This labeled will be ingested with other data for further analysis and processing. However, before we go more into the technical details of the additional data analysis and processing, let's briefly discuss the fundamental of big data. At the basic level, big data refers to large, diverse sets of information that grows. There are at least 5 key aspects. 1. Volume. The sheer quantity of data involved. 2. Velocity. The speed at which data is created and collected. 3. Variety. The scope of data points covered. 4. Veracity. The trustworthiness and quality of the data. 5. Value. The ability to provide actionable insights. Extracting meaningful information from the data, as in this case, for healthcare interventions, determines its true worth. As we go through the rest of this case study, you will see that we deal with 2 types of data: structured data, numeric and easily formatted. Unstructured data. Unstructured data, in our case image data, that does not fit into a predetermined model or format. However, it is interpreted with some form of structure for input and output of the machine. Apache Spark is a big data platform specifically designed to manage large, complex data sets. On the screen we show the setup of the Spark environment used in this ML development. The data from the patients is collected, but not all the data collected is useful or properly formatted. Additionally, when collected, there could be duplication in the data. Therefore, we first need to perform a process often referred to as extract, transform and load, ETL. We also need to do exploratory data analysis, EDA, to give us a better understanding of the data and how we will need to proceed with the data for AI/ML model development. Remember, our overall goal is to develop a model trained on electroencephalography, EEG, signals recorded from critically ill hospital patients. The desire is to have the outcome of our work possibly being adopted to rapidly improve electroencephalography pattern classification accuracy, unlocking transformative benefits for neurocritical care, epilepsy, and drug development. An AI/ML model like this may be used by doctors and brain researchers to detect seizures or other brain damage to provide faster and more accurate treatments. This would be extremely beneficial to the 3/4 of people with epilepsy in low-income countries that do not get the treatment they need, and this, as stated previously, rises to 90% in some countries. In many such countries, many health professionals do not have the training to recognize, diagnose, and treat epilepsy. An AI/ML model like this could be very valuable in scenarios like these, providing a first opinion diagnosis. This and the following screenshots show some of the ETL and EDA steps and demonstrate some aspects of the big data being handled.
In the frame just shown, we had 106,800 rows of data ingested in that one PySpark data frame. Here we show some imported sets of Parquet files. Parquet files are a form of file structure that stores information in columns. These Parquet files imported contain 17,300 unique EEG IDs, and 11,138 unique spectrogram IDs. Each file imported may have had as many as 500,000 or more rows of data. From the 11,138 spectrogram parquet files imported, we ended up with 4,279,506 rows of raw spectrogram data ingested. In this next frame, we show that from the 17,300 unique EEG IDs files imported, we ingested 280,905,200 rows of raw training EEG data. We subsequently dropped nulls and duplicated values, leaving 279,569,419 rows of EEG training data to work with. Joining these separate datasets can lead to billions of rows. Apache Spark is very suited to managing this size and complexity of our data. Now that we have completed some ETL and EDA processes, we next want to visualize some of the data. Visualization of the data helps us to understand the data in more detail and provide early insights as to the information at hand and how we may want to proceed with it to achieve actionable outcomes. The electrical signals that are emitted by the brain during a seizure are based on different frequencies in wavebands. In our case, we are concerned about 4 different wavebands between 0 Hz and 20 Hz frequencies. In this frame, we show 2 of these 4 wavebands for a specific spectrogram ID. On the right side, we show a plot of values at frequency 1.176 Hz within the delta waves range of 0.5 to 4 Hz and values of frequency 5.96 Hz within the theta waves range of 4 to 7 Hz. In the second frame, on the right side, we show a plot of values at frequency 15.43 Hz within the beta wave band. On the left side, we show a plot of values at frequency 9.96 Hz within the alpha wave band. Neurologists, the annotators, of EEG readings in our label data based their interpretation of seizure types based on the magnitude and frequency within the 4 waves bands. Although not shown in our plots, another set of data annotators used were EKG, recorded electrical activities of the heart, and this has been included in our analysis and AI/ML modeling. Once our primary ETL and EDA processes were completed, our next step in the process was to have prepared one final master data frame that contained more than 420 columns, features, and millions of rows restructured by data engineering process. Here we show a split view of that final master data frame. Here we also show the final data frame being split in train and test datasets for our first AI/ML model.
Let us now shift our focus to compare the difference in our Apache Spark AI/ML approach to the other approach predominantly used by the other 17,133 entrants who made 62,509 submissions to Kaggle. This one dominant approach used was based on a one-path structure. It used only a subset of some of the data. In some cases, some of the features were never used at all in their model development. For the data used, their approach was to convert spectrogram to EEG data and then to image. They then used the generated image to do model prediction of the classified seizure vote types. In this, our Spark approach, we adopted a two-path structure. We also used all the data and all the features, more than 420, in our AI/ML model development. On one path, we converted the spectrogram to EEG data and then combined it with another set of EEG that Kaggle had provisioned as part of the entire predictor datasets. This combined dataset was then used to do our PySpark AI/ML model development. On the other path, we generated images from the converted spectrogram to EEG data, but another difference here is that we did not use the image as part of our model prediction of the classified seizure vote types. We considered the image as a byproduct of our upstream process. The purpose of our image generation was to provide annotators with a visual, something they're familiar with, to triangulate against the EEG data the AI/ML model was using. Earlier, as provided by Kaggle, we indicated that there were different levels of expertise of the annotators, neurologists. This impacted the consensus quality of the labeled data for each of the 6 classified seizure vote types. Each EEG ID with an aggregate vote count of 10 or more was considered better quality consensus labeled data. For EEG IDs with aggregate vote count of 3 or more, the quality of consensus labeled data was considered inferior. With this in mind, we developed 2 different AI/ML models. This first AI/ML model presented here is a gradient boost tree ensemble model. A gradient boost tree, GBT, is a machine learning algorithm used for both classification and regression tasks. GBT leverages the collective strength of multiple decision trees to enhance prediction accuracy. This AI/ML model was built using a pipeline with different transformers such as string indexers, one-hot encoders, vector assemblers and GBT. We then predicted against data and concentrated our analysis on the test data predictions. Therefore, we will now shift our focus to analysis of the predictions. In our analysis, we are going to look at each of the 6 vote type predictions. The first one we will look at is the vote type seizure vote, labeled here as AVG_seizure_vote. The green highlighted column to the right shows the average row values made by the annotators for each EEG ID. This column is the data against which our AI/ML model needs to predict. The green highlighted column to the left shows the average row values our GBT/ML model has predicted for each corresponding EEG ID. It should be pointed out that throughout the analysis you may observe the same EEG ID in different rows with different target and prediction values. This is because there are different label IDs used to identify the annotator's labeling of the data. In addition, there are spectrogram and patient IDs being considered against each EEG ID. The second frame shows the vote type LPD vote, labeled here as AVG_LPD_vote. The green highlighted column to the right shows the average row values made by the annotators for each EEG ID. This column is the data against which our AI/ML model needs to predict. The green highlighted column to the left shows the average row values our GBT/ML model has predicted for each corresponding EEG ID. It should be pointed out that you may observe the same EEG ID in different rows with different target and prediction values. This is because there are different label IDs used to identify the annotator's labeling of the data. In addition, there are spectrogram and patient IDs being considered against each EEG ID.
This third frame shows the vote type GPD vote, labeled here as AVG_GPD_vote. As before, the green highlighted column to the right shows the average row values made by the annotators for each EEG ID. This column is the data against which our AI/ML model needs to predict. Also, as before, the green highlighted column to the left shows the average row values our GBT AI/ML model has predicted for each corresponding EEG ID. Again, it should be pointed out that you may observe the same EEG ID in different rows with different target and prediction values. This is because there are different label IDs used to identify the annotator's labeling of the data. In addition, there are spectrogram and patient IDs being considered against each EEG ID. This fourth frame shows the vote type LRDA vote, labeled here as AVG_LRDA_vote. Here again, the green highlighted column to the right shows the average row values made by the annotators for each EEG ID. This column is the data against which our AI/ML model needs to predict. Here, as before, the green highlighted column to the left shows the average row values our GBT AI/ML model has predicted for each corresponding EEG ID. Once again, it should be pointed out that you may observe the same EEG ID in different rows with different target and prediction values. This is because there are different label IDs used to identify the annotator's labeling of the data. In addition, there are spectrogram and patient IDs being considered against each EEG ID.
This fifth and penultimate frame shows the vote type GRDA vote, labeled here as avg_grda_vote. Here again, the green highlighted column to the right shows the average row values made by the annotators for each EEG ID. This column is the data against which our AI/ML model needs to predict. Here, as before, the green highlighted column to the left shows the average row values our GBTI/ML model has predicted for each corresponding EEG ID. Once again, it should be pointed out that you may observe the same EEG ID in different rows with different target and prediction values. This is because there are different label IDs used to identify the annotator's labeling of the data. In addition, there are spectrogram and patient IDs being considered against each EEG ID. This is our sixth and final frame, and it shows the vote type other vote, labeled here as avg_other_vote. As we have used in all frames before, the green highlighted column to the right shows the average row values made by the annotators for each EEG ID. This column is the data against which our AI/ML model needs to predict. RR in all frames examined before, the green highlighted column to the left shows the average row values our GBTI/ML model has predicted for each corresponding EEG ID. Once again, in this our final frame, we want to remind you that you may observe the same EEG ID in different rows with different target and prediction values. This is because there are different label IDs used to identify the annotator's labeling of the data. In addition, there are spectrogram and patient IDs being considered against each EEG ID.
Throughout our analysis of each of the 6 vote type predictions we had examined, at least one dominant theme would have been observed. Our GBT model was fairly accurate at predicting against target AVG vote values for each vote type aggregate count. In this frame we bring to your attention one EEG ID row prediction comparing the target value to the predicted value. Here we highlight the startling accuracy that the GBTI model can achieve. This particular case, the accuracy was 99.9%. The Kaggle competition was assessed on KL divergence accuracy. KL divergence is simply a comparison of the difference between the probability of set A relative to set B, in this case, the probability between target and predicted values. This is achieved by establishing ground truth, fraction of vote type, relative to total vote on each row, and comparing it to the new fraction based on the predicted value. The highlighted green section shows the ground truth and the highlighted orange section shows the predicted reality. The accuracy of each row prediction will be different. However, based on our observation of the prediction on the training dataset, we are relatively confident that our model is not generally overfitting or underfitting against our test dataset.
We will now briefly discuss and analyze the AI/ML model we used for the scenario where the quality of the consensus-labeled vote by the annotator was not as good. For this scenario, we used a different AI/ML model called Random Forest. Random forests, RFR, are ensembles of decision trees. Each tree in a random forest is trained independently on different subsets of instances and features. The idea is that the collective decisions of multiple trees lead to more robust and accurate predictions. Our choice to use RFR in this scenario is because in general it provides more robustness due to parallel ensemble approach. This should improve accuracy compared to a single decision tree approach as used in GBT. Here we show the RFR prediction for a specific EEG ID. The yellow highlighted area to the right shows the target values, against which the yellow highlighted area is showing the corresponding RFR predicted values.
Thus far we have discussed the GBT and RFRI/ML models separately. We mentioned that we had used them in different aggregate vote count scenarios. Each model had its advantages relative to the use case that was under consideration. Nevertheless, in both modeling scenarios what we did was to have the machine learn from the expert annotators and then mimic them in seizure vote type predictions, with the aim to be at least as accurate and have better consensus outcomes. We will now compare the model's performances against a specific EEG ID. In this frame coming up, the top portion of the frame shows the results of the GBT model for a specific EEG ID when looked at from a data frame perspective of the GPD vote type. The bottom portion of the frame shows the results of the RFR model for the same EEG ID when also looked at from a data frame perspective of the GPD vote type. We have highlighted in green and yellow the target values against the predicted values respectively. We observe that both models are fairly close in their predictions and are relatively accurate when compared to the target vote counts. A point of observation that is common across both the GBT and RFR-ML models is that the label _ID does matter with respect to the predicted outcome. This is consistent with the preparer's caution of the label's vote counts that the quality of the consensus vote counts is a factor to be considered. One of the differences we pointed out earlier with this distributed Apache Spark approach to harmful brain activity classification vote prediction compared to the one predominant approach adopted by Kaggle is with the use of images generated. In our case, we did not use the actual image generated in our predicted models. However, we did generate EEG images with the data. Therefore, at this juncture we will compare the images from both approaches. In this frame, the first image shown on the left is the image generated by the first-place Kaggle winner. The image shows the EEG signal observed based on the converted data as executed by the Kaggle winner. The second image, shown on the right, is the image generated by this Spark approach. This image also shows the EEG signal observed based on the converted data as executed under this method. It should be observed that the EEG images for this specific EEG ID are quite similar in terms of the wave patterns. The next few frames show EEG images for 3 different EEG IDs as generated by this Spark approach. Each frame shows 4 EEG images for each EEG ID. These 4 images show electrical behavior for each of the 4 chains. 1. LL representing the left temporal chain. 2. LP representing the left parasagittal chain. 3. RP representing the right parasagittal chain and 4. RR representing the right temporal chain. These positions were earlier explained when describing how neurologists interpreted signals and the signal's positioning on the brain during data capture. Based on these observed images, we may conclude that this Spark approach provides similar images information as would customarily be viewed by a doctor, the annotators, in order for them to make determinations on a patient's condition and the seizure type that the particular patient may have experienced. This third frame shown here, of the 3 reference frames, is for the 4 corresponding images for EEG ID equals 16770538845.
We have just taken you through a practical big data AI, ML, end-to-end model development approach for seizure and other harmful brain activity classification. The goal was to provide a different approach to predicting the total number of votes per classified seizure type using the Kaggle provided datasets. Therefore, let us now conclude our case study with following points. 1. A distributed computing big data approach with Apache Spark allowed for the use of the entire HMS harmful brain activity classification datasets for AI, ML model development and training. 2. Distributed computing with Spark SQL for structured data processing and Spark ML for machine learning provided us with a streamlined approach to an AI, ML model development. It allowed for us to have relied less on nuanced feature engineering and didn't require us to use extensive parameter tuning as other ensemble deep learning approaches. 3. We believe this model is comparable in terms of solutions results. Therefore, this ML approach can be a foundational starting point that can be improved upon, scaled, and subsequently pipelined into an automated process for EEG analysis. This approach may then help doctors and brain researchers to detect more efficiently, effectively, and accurately seizures and other types of potential harmful brain activities. This AI, ML approach and resulting models was the work of Dr. Michael Treasure. We want to thank Kaggle and the other competition sponsors for the dataset used. We also want to thank the Kaggle community that participated in the competition, as some of their efforts into calculating EEG signals from the raw data were incorporated here.